The next thing I want to look at, and this is in chapter 12 of the newer edition, is Huckel's rule. This is a way of determining if you have something that is aromatic or not. In general, what you're going to do is you're going to use a formula that's going to be your number of pi electrons equal to 4n plus 2. When you count your number of pi electrons in the entire molecule, you'll put that here, and then if your n value ends up being a whole number, then the molecule is said to be aromatic. Now this problem with the Huckel's rule, it only applies if you have a single type of ring structure. So you can't have multiple rings and use this particular formula to determine this. So if you have a monocyclic molecule that's planar, then you can use this particular structure. So if we look, so here's our basic rules right here. If you look at the benzene ring, if you count benzene ring, you can see that you've got 2, 4, 6 pi electrons. So if I substitute 6n for the number of pi electrons, solve for n, I do get a whole number, so therefore benzene is going to be aromatic. And you can see other types of molecules that are going to fall in that based on the number of pi electrons. Okay. Now the frost circle, I'm not sure exactly how useful this is, but it does show you a little bit about the bonding. So if you're looking at the benzene ring, that when you create the frost circle, you're going to put one of the vertices at the corners here and here, and then you'll put your lines at each of the carbons here and here, and the middle line is where your non-bonding electrons are. This bottom part is referred to as your bonding electrons. This is your non-bonding electrons. So when we did the molecular orbital model a long time ago, if you remember that, this is kind of set up the same basic way. Remember, your bonding electrons are going to be the ones that have the least amount of energy, so that's going to be where they would go in first, and then they would go in anti-bonding as necessary. So they'll pair down here, and then they'll come back and pair up here if necessary. So if we look at the benzene, here's our basic structure for our frost circle. Then we're going to put all 6 of our pi electrons can go down here in the bonding orbital. I'll have none in the anti-bonding orbital, so that makes it especially stable in this particular case. Now if I have something like cyclobutadiene, which is going to be a square type molecule, if I drew it, basically the molecule, it'd be something along this line. So I'd have 2, 4 pi electrons. So if I come up here and use my Huckel's rule, if I 4 equals 4n plus 2, and then of course it'd be 2 is equal to 4n, then my n is not going to be a whole number, right? So that means it's not going to be aromatic. If I come over here and look at this molecule, I'm going to put, and I'll do it down here, I'll put 2 in my bonding, and I'll put 1 in each of the non-bonding, because that's where this vertex ends up being, is in the non-bonding. Okay. If you have something like this where 2 of them are individual in this particular molecule in this model, then these are referred to as radicals. You have lone electrons, okay? So these will be a diradical type molecule. So 2 unpaired electrons referred to as being diradical, and he also referred to this molecule as being anti-aromatic. If you do the same thing with the cyclooctatetraene, then here's your basic molecule. So you can see you'd have 2, 4, 6, 8 pi electrons. So if I put it down in here, I'd have 2, 4, 6 in the bonding, 2 in the non-bonding. So this also would be a diradical and be antiaromatic. So there is a formula for antiaromatic compounds. If you want to determine if something is antiaromatic, you're going to use your number of pi electrons is going to be equal to 4n, and that's it. So again, if n is a whole number, in this case, it's going to be antiaromatic. So if I look at this one, I have 2, 4, 6, 7, 8 pi electrons equal 4n. N would equal 2. Therefore, this would be an antiaromatic compound.